Great. Okay. So yeah, so I'm gonna just pace it according to uh, how uh, people understand this, and if you want me to go slower at any point of time, just let me know, and I'll slow down. So that's not a problem. Okay. So let me start with how I got involved with Haskell and functional programming and my experience overall. So I've been programming professionally for about 12 years. I mostly, in JavaScript, Java, Ruby, Python, C, the usual things. But I also got involved with functional programming uh, like about 12 years ago, right? And I also organize the FP NCR meetup group. So if any of you guys are interested in taking this further along, you can join those groups, and I'll show you more details on how to join the group. But yeah, we really need more participation. I know there are lots of functional programmers in Delhi and Gurgaon, and who are just getting started, but they don't have any resources. So this is a good place to turn to if you guys are interested in functional programming. Yeah, so this is how my journey started with Lisp, as with a lot of people. SICP, structure and interpretation of computer programs, was how I got started with Lisp, and Lisp and Scheme. And but Lisp and Scheme are both dynamically typed, uh, sort of functional, not really quite the best functional programming language. A really good language otherwise. Uh, but it introduced me to the concept of code as data. So, first class code that you can pass around to other functions and manipulate. So that was a pretty powerful concept. And then after that, I discovered OCaml and Erlang. OCaml introduced me to static typing, which is again a really powerful concept. And Erlang introduced me to like concurrency and actor model and message passing and those things. Like how do you structure your program in a functional manner. So those things were really helpful. And then I came across Clean. Clean was uh, entirely an academic project. It still is an academic project. It has a lot of things that Haskell still doesn't, and including an IDE and great Windows support and great libraries. So Haskell still doesn't have quite a few of those. And Clean was a mind-blowing experience. It has very good documentation. It has a user manual which is pretty comprehensive. It has lots of tutorials, and Clean is very, very similar to Haskell. So that was my precursor into programming with a pure statically typed, lazy, modern programming language. And then I, of course, discovered Haskell, and I never looked back. So Haskell is, something that I've kept going for over a decade now. Like dabbling with it, not working with it professionally, but over the past couple of years, I've been working with it professionally as well. And now, of course, there are Elm, PureScript, and countless other new functional programming languages that are coming up. And I tend to dabble with a lot of those. But yeah, it's an exploding field. Even though it's an old field, it's like 1980s when it started. But it's a good thing to get into at this stage. Um, so yeah, these are the links. I just wanted to quickly mention the group that we have. So we have a GitHub organization. We have a meetup group. So you guys can just take a note of these. Um, so let's start with the basics, right? This is for absolute beginners. So what is functional programming? It's programming with functions, obviously, but I think at the core of functional programming is modularity. Uh, Functions is just a way of demarcating code, abstracting over code, and saying that this is my unit of abstraction. And functions is pretty much the simplest way in which you can abstract code, right? Everything else, like classes, oops, uh, actor model, everything else has to be built upon functions. So, in a way, functional programming is the simplest model that you can have. What it allows us to do is compose functions in a way that's very highly abstracted and that's very modular, and it leads to better software design. So the reason why functional programming is becoming popular is that we take those uh, things that we learn on how to construct a program functionally, and then we can apply that thing to every other language because every language has those functions. And what I plan to do right now is to give you a taste of how functions help us structure code. And it's not just if you want to do a thing, then you put it inside a function and that's done. No, so you have a lot more abstractions that you can build on just pure functions, and I want to explore those in these slides. So the primary thing that you should have in a language to be able to do this is functions have to be first class. Functions should be values that you can pass to other functions, and those other functions should be able to do something useful with the functions that are passed in. And obviously Haskell does that. There are several languages that don't. For example, C doesn't have this, and Java doesn't have this. But lots of languages, especially dynamic languages like Python, Ruby, and all, they all have this. Um, so yeah, so let's look at a simple function. This is Haskell syntax, obviously. All the code samples are going to be Haskell. And this looks pretty simple. This is the Fibonacci function. It basically gives you the nth Fibonacci number. And if you look at the first line, that gives the type signature of the Fibonacci function. So it takes an integer, which is the nth Fibonacci number that you want, and then it gives you the number itself. So the double colon that you can see there is a way of saying type of. So if Fibonacci has the type of integer to integer. The arrow says that it gives me something. So Fibonacci is a function that takes an integer and gives you an integer. That's how simple types in Haskell are written. And when you want to define it, Haskell being derived from it having mathematical roots, it has a very terse mathematical equation syntax for functions. So this is how you write it. You just basically write fib of 0 is 1, fib of 1 is 1, and fib of n, where n is a variable, is fib of n minus 1 and plus fib of n minus 2. Right? This is pretty much the simplest definition that you can write for the Fibonacci function. And questions about efficiency and stack overflows aside, this looks pretty reasonable, right? So this is how you write a very, very simple function. But Haskell has a few more things to make this, to allow more flexibility. I mean, Fibonacci is easy, but there may be other complications with other functions. So one thing that it does is that it has a case expression. Case expression is basically what the previous definition boils down to. So this is the actual definition of the Fibonacci function, where when you call Fibonacci on a number n, then you check n. If it's 0, then you return 1. If it's 1, then return 1. If it's n, then return the previous two Fibonacci function numbers summed together. So this is, a pretty declarative way of defining a function. Another thing that Haskell provides us is guards, and guards where you can have something like you can have, it's like an if condition. So Haskell has if then else, but it's not really used because we have guards. So you basically say fib of n if n is smaller than 2 is 1, otherwise it's something else, right? So these are various ways of defining the same function that we've already seen. And finally, you can effectively, even though this is a definition, in Haskell, everything boils down to anonymous functions. So this is exactly equivalent to this definition of fib, where we're saying that the Fibonacci function is a function, and then we use the anonymous function syntax for defining the function. So we say it takes a variable n, and then it has the case statement as we saw earlier, right? So I hope everyone understands this part, right? This is a basic function definition in Haskell that translates well to almost any language, right? Maybe except Python and probably Go, but lots of languages have similar constructs for anonymous function definitions, for pattern matching, and so this should be fairly simple. One thing that Haskell provides that most other languages don't provide are tail recursive, like proper tail recursion. So here we are calling Fibonacci function recursively, like fib calls fib n minus 1 and fib n minus 2. That is efficient in Haskell. So you can write this function as is, and it would not be too problematic. It would still have a problem of having to compute the Fibonacci of a number again and again, but it would not run out of stack. So this will run in pretty much constant stack space because Haskell compiler will optimize this for us. So it may not be the most efficient code, but this is a fairly reasonable way of writing the Fibonacci function, right? So yeah, so that's the basic criteria that for a functional programming language, it should have first-class functions, it should have basic pattern matching, and you should be able to pass functions around, and that's in lots of languages. But what makes Haskell unique is that it's strongly typed. So unlike something like Clojure, it has strong typing, and we'll discuss what strong typing means later on. It's pure, which means you can't do arbitrary, you know, IO statements. By IO, I mean like print something to the terminal or get user input. You can't do those things arbitrarily inside other functions, right? So it's pure. And it also means immutable. So like any data structure that you have, it cannot be modified. You have to create a new copy of the data structure. And the Haskell compiler optimizes that for us. And finally, it's also lazy, which means that you can potentially have infinite data structures, structures that are really huge, but you only access a small part of it, and the compiler will optimize it so that it doesn't even create the rest of the data structure, right? So it's by lazy, it means it only does things when it really has to, right? So these are three things that I think make Haskell unique. Clean also has that, but Clean is kind of an old project now. Uh, but Haskell is pretty much unique in that it has these three things. And we're gonna take a look at some of these examples as we go along. So the most important of these is obviously strong static typing. And the reason why we have strong static typing is that we want to catch errors earlier, sooner rather than later. So in Haskell's case, a lot of errors are caught at compile time instead of at runtime. And it's it's not just type errors like Java, right? So it's not just int that doesn't match with bool. Haskell types are a lot more powerful, so you can catch a large number of use cases where things would pass scrutiny in other languages but would fail Haskell's checks. Uh, an example that comes to mind is that sometimes Haskell will catch infinite loops because when you have an infinite loop, then it is not able to determine the types properly, and then it says something is wrong, right? And even though the types should match, but they don't because because of the infinite loop. So infinite loop is purely a runtime thing, but Haskell is able to detect that in some cases because of the typing. And usually people say that if because of the strong static typing, if it compiles, it works, and that is true to some extent, but it's a little bit of an hyperbolic statement where if you rely on just the compile errors to tell you if the program works, then there will be some times where you would have some logic errors or something. So the thing that actually does happen that saves me every day is that I'm able to write a program that works and then refactor it. And if it compiles then, like if it was working earlier and I refactor it and it still compiles, then I'm very certain that the program is correct. Because it's very hard to break a program in Haskell and not generate a type error. So if it compiles, that means you did the refactoring right, but the original implementation may be buggy, right? So Uh, that really helps. And of course, the point behind all of this is that uh, you have a computer uh, that you're typing on, right? So you should be able to offload as much work to the computer as possible. Let the computer check as many things as possible. You shouldn't have to do mental mathematics or keep track of variables and pointers and all those things just to ensure that you've made all the changes that you needed to. So with Haskell or with most functional languages, you'll get this guarantee that refactoring is a lot easier, and programming is like 90% refactoring. So it really helps with that. So okay, so these are the things that Haskell has when it comes to strong static typing. It has primitive types like Java, where it would have integers and booleans and those things. And then it also adds a lot of other things that we'll look at one by one. So primitive types, it has booleans, characters, integers, strings, blah 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 blah, lots of them. Floats, for example, doubles. But it also adds a void type, right? So, and this is not an inbuilt type. This can easily be defined, but uh, basically a void type means that this is a type that can never have a value. So, like a Boolean value can be either true or false. A character can be either A or B or C or blah blah whatever. An integer can be 0 or 1 or 2 or 3 and so on. Uh, but a void type can have no values. So if a function returns the type void, then it can never return. So that's the sort of guarantees that Haskell provides, right? So if an API returns a value void, has a function that returns a void, then you know that that function will never return. The type tells us that this is like an infinite loop, or it'll error out, or something like that will happen. Uh, or if an API function uh, takes a value of type void, then you basically know that that function can never be called, right? So what good is that, right? But there are uses for functions like that. So uh, yeah, so we have a void data type. We also have a unit data type, which is basically just empty parentheses, and that has only one value, which is empty parentheses. So that's usually for when you want a function to be called just for the side effects. So like a print function will return a unit type because it doesn't return any useful value, but it just prints to the console. And obviously, it doesn't return just the unit type. It has because you can't just do I/O directly in a function. So there are some complications around that that I'll come to later. But in principle, it returns the unit type, and then you have the rest of the things. So uh, apart from the primitive types, there is also ways to combine them, and we call them algebraic data types, right? So algebraic means algebra plus uh, uh, sum, multiplication, so those things. So when you say sum of data types, you basically mean it can be either A or B, right? So it's a union of data types. That's what we mathematically we say the union of data types is the sum. And when we say product of data types, it's basically saying that we have both the data types. So looking at the first example, shape, right? A shape can be either a square or a circle or a triangle. And here we have the sum of square and circle and triangle. Because it can be either a square or a circle or a triangle. It can't be two at the same time or three at the same time. Uh, and similarly, we have user, who can be root or some other login string, right? So the string here is the username. So it can be either root or it can be some other login. It can't be both at the same time. So this either or kind of a thing is very very useful. You'll find data types like this everywhere. For almost everything, you'll need to enumerate cases. Some languages provide enumerations like shape, but they don't allow parameters for those enumerations. So like for example, for user, we would like to store the username inside login. So when it's not root, then we also need to store the exact username. So Haskell allows us to do that. And this is the syntax. The syntax should be pretty self-explanatory, where you have data, that's the keyword, and you define the data type name, and then you enumerate all the values that it can have. They're all separated by this pipe symbol. Um, and then, as I said, you can have parameters. The unique thing about this is that you can also have uh, what Haskell calls polymorphic uh, parameters, but you can just think of it as variable, right? Variable parameters. So, for example, we have a data type that's built into Haskell. I mean, in the standard library called maybe. So maybe of uh, a, you're defining maybe a, which means it's either a or it's not a, right? It's nothing. So that's a possibly a cute way of defining this, but what we're saying is that when you have a value of type maybe a, it's either just a or it's nothing, right? And if it's just a, then you can extract an a out of it. If it's nothing, then you can't extract anything out of it. Similarly, we have another data type that's uh, either, where when you want to say either A or B, right? So Haskell provides tags left and right to the either data type. So uh, when we say that it's either A or B, it's either left A or right B, right? And you can check which one it is, like if it's left or right, and get the corresponding value. And because of the type system, it'll ensure that if it's left, you can't possibly get a B out of it. Or if it's right, you can't possibly get an A out of it. And if you try to do any of those things, then it's a type error at compile time. So it will not be at runtime, right? Um, Another thing that Haskell allows us to do is have recursive data types. So this is how you could potentially define a list in Haskell. So uh, going back to our previous example of maybe, maybe is a type constructor, right? So it's basically takes a type A and creates another type called maybe A. Similarly, list here is also a type constructor. It takes a type A, which could be anything. It could be integer, string, character, whatever, and it gives you a list of A's. So a list of A, you can read it like this. A list of A is either empty or it's uh, the value A and further elements in the list, right? So that's called cons, where you have a head element A and then you have the remaining elements in a list. So this is how you would define a list, and that's a linked list. That's not an array, but a linked list. And the internal list data type that Haskell provides is also very similar to this. You can use this instead of that, but the internal one comes with special syntax, so that's kind of helpful. Similarly, if you wanted to define a tree, it's again simple. A tree is either a leaf, uh, and a tree of values A, values of type A, is either a leaf with that value A, or it's a branch with the left tree and the right tree, right? So it should be fairly, it should, I mean, once you get used to the syntax, it should be fairly intuitive how this tree works. And lots of other languages will have lots of syntax, and which will make it more difficult to grok what exactly is happening in the data type. But Haskell, or functional programming rather, puts data types first. So the syntax for defining data types and defining functions is extremely clear. It's the clearest possibly that you can get, right? So you just enumerate all the cases that you can have. So looking at the tree data type again, you can see that it's a sum of leaf A and the branch tree A, right? So it's a sum because it can either be a leaf or a branch. But going inside the branch, you can see that it's uh, composed of two trees, the left tree and the right tree, and they are. It's not either left tree or the right tree. It's left tree and right tree. So that's the product, right? So the tree data type is basically sum of a product, right? So and that has parallels in normal algebra, where when you write like A into B plus C into D, right? So you have a sum of A into B and C into D, which are products. So that's how you define data types also. And some of the identities like the associative law, distributive law, those things also apply to data type definitions in Haskell. But that's probably out of that's for a later discussion. But uh, so it has a mathematical basis in why we are calling them sums and products. Um, so is this clear so far? Should I move on, or does anyone find this a bit difficult to follow, or possibly explain something else? Everything clear? Okay, I'm gonna move on. I have lots of slides, so I can take it to as till whatever point you guys want. So, okay, so this is an example of first class functions. I mentioned first class functions. I mentioned passing a function to another function, but I didn't show you an example of that because I wanted to show you data types first and then show you how to write a type signature for a function. And so now you should be able to understand this, where we define a data type called ordering. And this is again in the standard libraries in Haskell. So I'm defining it here, but while programming in Haskell, you don't need to define these. So an ordering means an ordering between two values. So let's say you have A and B. So either A is less than B, that's LT, or A is greater than B, that's GT, or it's equal to B, that's equal to, right? So uh, uh, that's a data type that we have. And then we define, okay, so here I have a type keyword. So type basically is just like defining a synonym. And I'm here saying that in the rest of the code, whenever I see uh, comp is like a comparing function. So whenever I see a comparing function A, replace that with this thing, which is that comparing function A is basically a function that takes two values of type A and returns an ordering. So it tells me whether the first value is less than the second value, or greater than the second value, or equal to the second value, right? And So I've just defined the synonym because it's much easier to use the synonym rather than type this entire thing everywhere that I use it. And then if I have a sorting function which takes a list of A's and sorts them and then gives me the sorted list back, right? I can have that function take a comparing function so that it knows how to sort correctly, right? So uh, to write a generic sorting function, which will work on all data types, you would require that function to take a comparing function. So that if you want to do it for integers, like sort a list of integers, then the comparing function would be specialized for integers, right? So it will just compare the integers and return LT, GT, or EQ. Or if you wanted to define it for your own data type, like for example, let's say we were defining a comparing function for the user data type that we saw earlier, where the user is a root, or it's a person, it's a username, right? So in that case, you may decide that, okay, I want these types to be sorted in a way so that root is at the top. Uh, uh, I mean, root is bigger than everything else, and then when you are comparing users, then you just compare their usernames as strings, right? So if you will just define a comparing function, call it like user compare or something, which will have the type CMP user, and it will take two data types, and you will check if both are root, then they're equal. If one is root, then that one is bigger, and if both are users, then they just compare their usernames, right? So you can define your own comparing function, and you can pass it to sort, and then you can pass it a list of users, and it will give you a sorted list. So sort is like a generic function that you can define, um, and that takes another function as an argument. So yeah, sort is also again inbuilt into this, so you don't need to define it. But if you wanted to define it, you could. Okay.
One question. One question, Anupam. So,
Yeah.
where's the logic of the sorting here? Like, for example, if I'm sorting the custom object, like what you're telling about the user objects,
Right.
or if I'm sorting the integers, I'm sorting the doubles. So, where's the logic defined? So that we have to define it,
Yeah,
obviously, right?
this is I was just showing the type signature of sort. So I mean, if you're defining sort yourself, then you would have to define the logic. But that logic will have like several lines of code, and then you would have to use some kind of an algorithm like quicksort or something. That would have complicated the thing. So I'm not showing it here, uh, but you would define it in a way that's totally generic, right? So I mean, sort is
Mm-hmm.
also defined inside the standard libraries. So if you want,
Okay.
you can just use that. But if you wanted to, like for learning or for whatever purpose, you wanted to define it yourself, then you could, and it would have this kind of a type signature. Uh, so it would be totally generic, right? So here A could be anything. It could work for integers, it could be for strings, it could work for anything, right? All the sort function is saying is just looking at the type signature. The sort function is saying that if you give me a comparing function and a list of those objects, then I can sort them, right? I don't need to know
Okay.
what those objects are, right? So this is very similar
So it's like
to.
abstract, right?
Right, just like you would, for example, define if you wanted to do this in Java, for example, right? So you would define an interface or like an abstract class, which would be something like comparable, right? And it would have a function called compare inside it, and then each
Mm-hmm.
subclass could implement it differently, right? And
Yeah.
then the sort that you would define would use the comparing function and then just do it. So this is how you would do that in Haskell, right? Without having access to
Fine.
uh, inheritance and subclasses, because Haskell is not object oriented, right? So uh, this is how you could. This is one way of doing it in Haskell
Yeah.
with just using functions.
And yeah, I think I got it now. So another question is like in Java and C Sharp, right? We have the concept of generics, and I think
Right.
I'm really missing those here. Is it like because we don't need the generics here because I mean we don't need type erasure and generics kind of a thing
So
in Haskell?
so generics are don't they serve the same purpose as this A here, right? So for example, using generics, you would say a list of T, right, where T is
Yeah,
not
yeah,
defined. Right. So here also,
yeah.
like while sorting, you're saying a list of A and A is not defined, right? So the sort function works for
Yeah,
any list.
I got it. I mean, it's a different way to represent it, right?
Right, right.
That's what you're saying.
And the important thing here is that Haskell has the same capabilities, but it doesn't have a lot of syntax around it. It just is
Yeah.
cleaner to write. So you can focus on the
Hmm.
logic.
Got it.
And also in Haskell, so this is called polymorphism in Haskell, right? And normally when you think about polymorphism in something like Java, you would think of ad hoc polymorphism, where you would define an object with some functions, with some methods, and then you would subclass it differently and override those methods for the subclasses. And then when you pass that subclass to a function or another method, then depending on which actual subclass was passed, it will do different things, right? So
Yeah.
that's what you would call uh, uh, ad hoc polymorphism in Haskell, right? So that is
Hmm.
a very basic way of making things polymorphic. But this way of making things polymorphic, where the sort function doesn't care about the object at all, it just says give me anything as long as it has a comp function, and I can do this. That's a stronger kind of polymorphism. The distinction is kind of subtle, but it's real polymorphism rather than ad hoc polymorphism. The difference is that with ad hoc polymorphism, you it only works for the subclasses that you have defined, right? But with the real polymorphism, it works for anything, right?
Anything. Yeah. Got it.
So that's the difference, and the advantage that it gives us is that with real polymorphism, you get a lot of compile time checks and a lot of proofs that you can have. So, for example, looking at the sort function, because we are not passing anything else except the comparing function, so you know for a fact that it can't do anything else with a. So if we pass it a list of integers, then you know that it can't like increment the integer or sum the integers and do something else with that sum, right? Because the sort
Yeah.
function doesn't know anything about the object that's passed except that it has a comparing function.
So you cannot mutate anything, right? That's what you're saying.
Mutate also, and also for example, you can in Java you can write a sorting function for integers that just gives you the head of the list. I mean the first element of the list, right? So you say
Yeah.
sort 3 to 1 and it just gives you a list of 3. There's no
Oh,
way to
yeah.
say that if it's doing the right thing, right? But
Hmm.
in sort here, you know that it can't do. So okay, so head this can also do, right? Because again,
Hmm.
if you the sort function could do anything, right? But for example, if it was doing something like adding all the elements together and returning. So if you say sort 3 to 1 and it just adds everything together and gives you a list of 6 just with one element 6 inside it, right? So that is
Yeah.
disallowed by this because it can't know that it's being passed an integer. Whereas possibly the
Hmm.
sort implementation for integer could do that in Java, right? So some classes of errors are prevented in Haskell because of this, because of polymorphism.
Okay. Got it.
Okay, and I was coming to inheritance because the thing that's missing with Haskell, I think most of the object oriented stuff, the advantages of object orientation is abstraction, encapsulation. You have all those things in Haskell, but what people miss is inheritance. Like, I want to be able to define a vehicle and then a car, which is a subclass of vehicle, and then a racing car, which is like a subclass of car. So you don't have those. What Haskell forces you to do is have a data centric view. So if you're defining a racing car, you have to think of the essential properties of vehicle, like what makes a vehicle, and take that data out, abstract that data away, and put that inside racing car. And then whatever makes a car beyond what makes it a vehicle, right? So take that data also out and put that also inside the racing car. So you basically compose things instead of inherit from things. And the advantage that you get from this is that a lot of times inheritance is very inflexible, right? It seems like a good way to structure things, but it as you write more code, it becomes inflexible. You'll realize that it's that inheritance diagram doesn't quite match the real world, so you have to have some more things, and you it doesn't match one to one with the nouns in your project, right? So you have to have some abstract classes here and there and some interfaces, and it becomes very complicated. But whereas if you do composition, and I don't have any specific examples of why this is easier, just that in practice I found this to be a lot easier to think about and a lot more scalable. So you define it like this, and then if you want to specialize it further, you again take the racing car data and put it inside that thing, and it just is infinitely scalable and with no drawbacks really that I can see so far in practice. Okay, so I've defined data types and I've shown you function type signatures. Now let's just see how functions are actually written, right? And everything that I will show you is going to be pure functions. Functions that take in some data type and return some data type, and they can't do any mutation and they can't do any I/O. So they can't like print anything to the console or delete some file or even read some file. They can't do anything like that, right? So uh, you may, while you're going through this, you may have the question of how do you do anything useful in Haskell, right? So we'll come to that later on in the slides. So, okay, so let's say the problem is that you have a list data type. I'm repeating it here for, so that you can see all of it at one go. You have a list data type and you want to take in a list and return the first element of the list. So that in Lisp terms, that used to be called car, right? Uh, I don't know how many of you are familiar with Lisp, but it used to have these car and CDR functions. and car would give you the first element of the list, and CDR would give you the tail of the list, which is everything except the first element. Uh, and so let's try defining those in Haskell. So the very first thing that you do is you write the type signature. So type signatures are easy here. Car on line 9, you can see that car takes in a list of A, and A could be anything here, and gives me an A, right? So it takes the first element of the list and returns that. Now again, polymorphism comes into play here. It could be a list of anything, right? I don't have to subclass from a list container or something, right? So if I have a list of something, I can pass it to car, and it will give me the first element of the list. And similarly for CDR, we can define the type signature very easily. If I have a list of A, it will give me a list of A, but that list of A will not have the first element. It would have the rest of the elements. So type signatures are easy. When you're defining the actual implementation, then you have to go case by case. For each option in the data type, so here you would have the list can be either empty, or it could be a cons of 1A and the rest of the list A, right? So for each of them, you define a case. So you would say car on line 10, you would say car of empty is what? Now, what does it mean to take the first element of an empty list? We don't know. So I can just put question marks here, and I'll come back to it later, right? Then we start defining what it means to take the first element of a cons. Now with cons, by definition, it says that the first element is the first argument to cons, and the rest of the list is the second argument to cons. So here I'm saying that when you take the car of a cons, you just return the first argument directly. And underscore is special Haskell syntax that basically means that I don't care about this other argument, right? So because I don't care about the rest of the list. So if I already have access to car, to the first element of the list. So does the definition of car make sense? It's like a straightforward literal translation of the definition that we want. And for CDR, you again, what does it mean to take the rest of the elements of an empty list? Again, I'm not really sure, so I'll put question marks here. And then, but the second case is easy. If I have a cons of the first element and the rest of the element, then the result is just the rest of the element. I get rid of the first element, right? And now we need to think about what to fill in into those question marks. So does anyone have any idea for, let's take CDR first. What can we put in place of the question marks on line 6? What should be the result when you take the tail of an empty list?
It's maybe like a maybe dot none or something. I don't know.
Well, yeah.
Nothing.
So you can return none, right? Or
None.
in a language with nulls, you can return null or something, right? But with Haskell, with this data, with this type signature, you can't do that because you're supposed to return a list, right? The type signature
Oh, okay.
forbids you from returning anything else except a list.
Well, otherwise it will complain if I return none.
Yeah,
Because
it will not compile.
you want,
because
yeah.
that's the point of static types.
Yeah, got it.
So we will initiate a new list in this case.
Well, there is no in Haskell there is no concept of creating something new, right? So I mean, so a new list is just empty, right? So think of it as that there is one empty that's already defined and it's always there, right? Empty has no arguments. So any empty is the same empty, right? So there is no difference between creating something new. Like you can't create two empties which are not equal to each other, right? So
Okay.
the tail
Yeah.
of empty, I mean, one way could be that just return empty, right? Like the tail of an empty list is just empty list, right? That's one way of
So empty
solving
is what?
it.
Empty is like, oh, because you have defined it empty.
Yeah, exactly. So you I'm
Yeah.
gonna move to the next line. So line 6, you can just say tail of empty is empty,
Empty. Okay, got it.
right? You can just say empty here. So
Yeah.
that's basically saying empty list, right? But okay, I'm gonna skip back to the previous slide. So, but when it comes to cart, no matter what we think, right, there is no way to write this function because the Haskell type system will prevent us from writing anything of this sort. And you can think about why that would happen. Given an empty list, right, and that list could be of integers, of strings, of whatever, but it doesn't have any elements inside it, there is no way to get an object of that type, right? I can't. So you might think that if I wanted to return the first element of a list of integers and that list is actually empty, then I can just return 0, for example, right? That if there is no element, then return 0, right? That's a very common thing that you would do. Maybe it's not that common. This seems a bit blatant, but you tend to write code like that when you're writing in other languages. That if the list is empty, then just return some default value, right? But Haskell will prevent you from doing that because it doesn't know what the type of the list is, right? It could be a list of integers, it could be a list of strings, it could be anything, and this code has to work for all types, right? So there's no way to return any default value, and Haskell doesn't have nulls, so there's no way that we can return a null or a nil or whatever, right? So when you start writing code like this, Haskell will force you to rethink your API, and then you will realize that car can't just return an A, it has to return a maybe A, right? And your API will automatically refine itself. So you will so for CDR, it's fine to return a list because you can return an empty list. You can create an empty list out of nothing, right? But you can't create an element of the list out of nothing. So you have to return a maybe A instead of A, right? And you will return a nothing. And then correspondingly, now you have to change the other case also on line 11. You can't just return an A, you have to return just A because all the cases have to uh, return the same data type. So everything has to say maybe, right? Does that make sense?
Yep.
Okay. And the other advantage of this is so now because of the type system, you have to refine your type signature, and you've done this. But the additional advantage is that uh, any code that uses this API will get a maybe A instead of A, right? So if it gets a maybe A, it's forced to deal with the fact what if maybe A is nothing, right? So whenever it has to use that A somewhere, for example, if we passed it a list of integers and we said give me the first element, it will give me a maybe int, maybe integer, right? And then if I try to use that integer anywhere, Haskell will give me a type error saying that this is not an integer, this is a maybe integer. And if it's a maybe integer, you need to extract an integer out of it. And while extracting, you will again write a code similar to this pattern matching code. And again, you would have to deal with the fact that it might be nothing instead of just.
Yeah, so you avoid basically the null pointer exceptions that we usually
Exactly.
get, right? With this,
Exactly. There's
yeah,
no way to have a null pointer exception in Haskell
null
because there
pointer
are no
exception.
nulls, right? But
Because you have to handle nothing, even if you have to do something. So you have to
exactly,
handle it. If it is
exactly.
nothing, I need to do something. Yeah.
Exactly. And the compiler will stop you from not handling it. It's not just a runtime thing, but it's a
Yeah.
compile time thing. So, and this is just a simple example, like maybe it's called optional or option in other languages. That's a
Yeah.
very, very common pattern. But uh, when you have access to this rich data type structure, then you have a lot of such patterns in Haskell, right? Which are not yet there in other languages. So they prevent a lot of errors that you would normally have at runtime. Okay, so I just wanted to show you another example of just to give you a feel of how Haskell code looks. And want everyone to notice that this is like simple, uh, concise code, right? So this is list concatenation. So on line 5, you start by writing the type signature. which, and this is slightly new. It now takes two arguments and then returns a third one, and we basically separate the arguments as well as the result by this arrow sign when we write type signatures. The very last value in the type signature is the result type, and all the previous ones are basically arguments, right? And there is a reason for why we do this, which I'll explain. So yeah, so basically, you can think of it as concat takes a list of A, and A could be anything, and takes another list of A, and then returns a concatenated list of A, right? And this is how we would define it. So you're forced to consider all cases here. You're forced to consider the case where both lists are empty. You're forced to consider the case where one list is empty and the other one is not empty, or if the second list is empty and the first one is not empty, and if both are not empty, right? So there should be four cases. I've written only three here on line 6, 7, and 8 because the first case of concat empty empty is automatically handled by the one on line 6. So it basically says that if the first list is empty, then the second list is the answer, right? So when you concatenate an empty list with anything, then that anything is the answer, right? It's almost mathematical in a way. Then on line 7, you're saying that if you have some list but the second list is empty, then the first list is the answer because empty is the identity, right? So you can append it either in the beginning or at the end, and it will return, the list will remain unchanged, right? So line 6 and 7 basically say that concatenating an empty list with anything else just does not change that list. And in the case that both list A and B are empty, then basically it will return an empty by line 6 because the first list will be empty and it will return the second list, which also happens to be empty, and it will just return empty, right? So and then finally, the final case that we really need to handle is when both are cons. And here is some additional syntax that I probably shouldn't have added here, but you can also do this at symbol, right? So when you say some variable name and at and then some data type, then basically you're saying that this entire argument is called B, right? So you can use B instead of typing the entire thing, cons, blah, 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 right? So basically here what I'm saying is that the second argument is B. But I also want to ensure that I also want to match it with cons so that it doesn't match with empty. That's why I had to do this B at thing. Otherwise I could just say B, right? So here in the final case what I'm saying is that if the first element, if the first list has the first element as X and then the rest of the elements as XS, and the second list is B, then when we concatenate them together, the first element of that list remains X, and the remaining elements are basically the concatenation of the remaining elements of the first list and the second list. Does that make sense? That may be slightly complicated to look at initially, but does that make sense? Basically, I'm recursively calling concat. I mean, so maybe I should open a simple text editor or something. Just to explain this more. So I'll just quickly run through this. So let's say the first list is 1, 2, 3, right? And I want to concatenate it with 4, 5, 6, right? So according to this formula, I'm saying when I concatenate these things together, and I'm going to call this plus, when I concatenate this together, then the result, and I start writing the list, has the first element as this, the first element of the first list, 1, and basically concatenation of the remaining list, which is 2, 3. So and the concatenation of the remaining list, which is 2 comma 3 plus the second list. It basically says this. Okay, forget the brackets, but basically this is what it says. Right? So the first element of the list is 1, and then to find out the remaining elements, you concatenate these two. So now the compiler will go and call this again, and the first element remains 1, and then for this one, it will say, okay, to concatenate these, take the first element of the second list, 2, and then to find out the remaining elements, concatenate these. So it will say concatenate 3, 4, 5, 6, right? And then the compiler will say, okay, now to concatenate these, you basically take the first element of this, which is 3, and then you take the remaining elements. Now, remaining elements here are just empty, right? This is how you say the empty list in Haskell, and then concatenate it with 4, 5, 6. Okay, and then the compiler will say, okay, to concatenate these, what I do is, now to concatenate these, I have to call concat, but the first list is empty here, so this case will be called. So this line 6 will be called empty b is equal to b. So when the first is empty, then the result is the second list, right? So it will, the remaining will become 4, 5, 6. So this is basically the mathematical definition of concatenation, list concatenation, right? To concatenate a list with another list, you basically recursively call concat with a smaller input than the previous thing, right? And the Haskell compiler will effectively convert this to a loop. So you can write this in this high level form, and then Haskell compiler will convert this to a loop, right? So it will be as efficient as doing it with a loop and like iterating through it. So this may not be totally clear, but we're going to discuss this more. So I'm going to just move on and continue to use this example. I just wanted to show what it looks like in Python, right? And if you look at the Python code, only lines 6 to 11 are the actual concatenation code. And I took this from the standard Python library. So this is what the actual Python concat looks like. I think I took this from the library. I'm not sure. I took it from some online source where you have a data cell uh, which defines the linked list, and then this is how you concat. So you basically start with the first element, and then while you iterate over the first list, and then when you reach the end where the first list has stopped, then you append the second list, right? So this is the standard way of doing it in an imperative language, a non-functional language, and you would write a similar thing for JavaScript or whatever, right? So while comparing these two solutions, look at Python. Python has lines 6 to 11, which is a fairly 6-line code, right? Fairly small chunk of code. And if you look at it, like you understand while and all those things, and the implementation of linked list, you put more or less understand that this looks fine. And looking at the Haskell code, again, lines 5 to 9, so it's 5 lines instead of 6, but effectively it's also almost the same size, and this may look slightly, maybe the same amount of complexity if you understand, how recursion works, and if you look at it enough, then you would say that they're about the same level of complexity. So why is this way of writing code better? Right? So again, side by side, Python is on the left, Haskell is on the right. Why is Haskell code better? And okay, first of all, does anyone think that the Haskell code is better, or or does anyone have any arguments on why the Python code is better? Do people think that Haskell code is better?
I mean, if your mindset is procedural code, I think Python is better, I would say.
Cleaner.
But yeah, if you change your mindset, if you change your mindset to functional programming or functional thinking, then obviously, Haskell is better. I mean, if I think about like I'm reading the code in plain English,
Right.
I find Haskell better. Yeah, if I
Right.
think that, I'm reading a code or something, I think Python is better. That's what I would summarize it.
Right. So Python code has lots of advantages. One of the things is that you understand what's happening. You understand how the machine will
Yeah.
execute this code. Right. So that is something that you don't get with Haskell, because the Haskell compiler will like totally modify this code to be able to run it on a real machine. So that's definitely a thing. And most people would say that, it's a matter of mindset, like procedural versus functional. So if you're used to procedural, then Python is better. Otherwise, if you're used to functional, Haskell is better. But let's move on to how a full software development lifecycle would look like, right? So you would then want to test your code, right? So both the pieces of code can be tested. Here I'm using a very Pythonic syntax. So you would say, then you would think of how you would test it, right? So you would say, okay, so let's say if and while testing, you would want to compare like empty strings, and you would have to test all those edge cases. So you would say, okay, let's say if the first argument to concat is empty and the second argument is bar, then the final result should be bar. Then you would come up with another test case, like if the first is foo and the second is empty, then the result should be foo. And if you're concatenating foo with bar, then the entire result should be foo bar, right? Like these standard test cases that someone might write just to test their code. Uh, and so you can write test cases like this. Now, if you look at this, looking at just the test cases, they look so different from the Python code, right? But if you look at the test cases and compare it to the Haskell code, they look very, very similar, right? I mean, in the number of cases and in the number of different things. Like you can write another test case which says, okay, concat of 1, 2, 3 with 4, 5, 6 is 1, 2, 3, 4, 5, 6. But are you really testing new information, right? For the compiler, foo is the same as 1, 2, 3, bar is the same as 4, 5, 6. We can be reasonably certain that if foo and bar concatenate together give me foo bar, then 1, 2, 3, 4, 5, 6 concatenate together will give me 1, 2, 3, 4, 5, 6, right? But the edge cases, these are really important. Like how does it handle empty values, or the first string being empty, the second string being empty, or even things being too long, right? You would like to test with like 200 characters or whatever your limit is, right? So here, just by looking at the test cases, you will realize that you eventually, while testing, you would think in a manner similar to how Haskell does it, right? So it's slightly better. It has that advantage there that when you write Haskell, you don't really need to test this code. I mean, you need to test this code if you want to, but the test cases will be very similar to the code itself, right? So if you're testing the Haskell code, just the first test, looking at the first test, you know that it will succeed. You don't have that surety with Python, because we know that it will succeed with Haskell because you explicitly wrote that code to handle the first empty and the second non-empty, right? Similarly, for the second test, you know that it will succeed, right? Because you explicitly wrote that code, right? So that's one of the ways in which Haskell is objectively better, that it matches very closely with testing. And that's mostly the reason why people say that, Haskell doesn't need testing. If it compiles, it works. But as I said, that's not really true. That's hyperbole, really. So it's only the third case that you really need to test, that the third logic of both the lists being non-empty, does that do what we want it to do? So you still need testing, but a lot of the testing is removed with Haskell or functional programming. And then the other advantage is granularity, right? So you have look at one line of code of Python and one line of code of Haskell and see if any of it makes sense. Like this is just a 3-line function, so you can look at it in its entirety, right? But if you had like a 15-line function or 20-line function, you can't look at all 20 lines in one go. So you would be looking at 3 or 4 lines at a time, and does it still make sense? Like if I'm looking at Python, I'm looking at current is equal to A. Does that still makes sense. I don't know. I have to look at the rest of the context to figure out if this line is correct or not, right? I can't be sure whether current is equal to A is doing the right thing or not. But by looking at Haskell, I know that this line is correct because concatenating A with empty gives me A. That just makes sense, right? So Haskell has a very modular approach to writing functions, right? So you can look at small pieces of the function and come up with this mental model of, yeah, this looks fine. I don't know how the rest of the function works, but this looks fine, right? So it's easier to debug, easier to refactor. If there is a bug in this one, you would be able to read just this line and say that this is the bug, right? So that's the second advantage that Haskell has. And the third advantage is kind of sneaky here. As I said, debugging, it really helps, right? The Python code has a bug, and you have maybe 5 minutes to figure out what the bug is. And the Haskell code may also have a bug. So if anyone can spot a bug in Haskell code, they can also tell me. But what is the bug in the Python code? And this is just like 6 lines of code, right? Can anyone tell me what the bug is here? Does anyone want to attempt? I don't want you guys to do debugging in the presentation, but it's not obvious, right? I mean, this I can look at each of these lines continuously, but if I didn't know exactly what the bug was, I can't come up with it. I mean, this might waste an hour of my time just debugging this, right? And when I tell you the bug, you'll probably say, "Hey, oh yeah, this is obvious," but otherwise. You would not be able to find it. So yeah, so the bug here is, I'm just going to reveal it. The bug here is that if you look at the actual definition, this one line number 10 is indented. It should be outside the while loop. If you change the current dot next to the second list directly, so you're basically setting the next for each element to B, so that you're just basically screwing up your entire list here, right? So this is not an easy bug to find. It's Python is white space oriented, and such white space errors are really, really hard to find, right? So this should be outside the while loop. And obviously, if there is a bug in Haskell, 99% of the time it will not compile. And if it compiles, you should be able to look at each statement separately and be able to find the bug. So yeah, so when you start coding more and more in functional programming, you realize you have all these things that did not show up earlier. So yeah, so I really like this statement. There are two ways of constructing software. One is to make it so complicated that by looking at it, you're like, this is fine. Like even during code reviews, someone code reviewing this will probably say, yeah, this looks fine. Yeah, you're doing something with pointers and something's going on and this looks okay. So it's complicated, but there are no obvious deficiencies and you're fine, code review done. Or the other way is to make it so simple that there are obviously no deficiencies. If I have the mathematical algorithm, if I understand this mathematical algorithm that, okay, to concatenate two lists, you take the first element of the first list and then concatenate the rest of the elements with the second list. If I know this, then this code has obviously no bugs. Just by looking at it, I can tell you that I don't need to test this. If I have that mathematical knowledge, if I have that algorithmic knowledge, then this code works fine. So yeah, so we are trying to move towards that, where every piece of code is so simple that you understand it and it's obvious that there are no bugs, right? Not just no obvious bugs. So yeah, and at this point, people usually ask me, fine, Haskell is simple, but if you start actually reading about it, then you encounter lots of mathematical definitions and lots of category theory, and this is an actual thing, like a bit tongue-in-cheek, but someone actually said that monads is just monoids in the category of endofunctors. Like, what's so hard to understand, right? So, but this is something that you can, like, this kind of things you can actually ignore. You can program in Haskell like you normally do in other languages, and still you would reap the benefits of functional programming. You just have to change your mindset a little bit to do functional programming. using functional programming algorithms on immutable data rather than doing while loops and all those things, right? So you can ignore all this and be highly productive. And the second thing that I really want to emphasize here is that there's this myth that functional programming or Haskell programmers are smart people. I honestly believe that I'm not smart enough to write code in other languages because it's just been so long since I wrote Python code, for example. And I've been doing like some JavaScript here and there, but uh, if I had to write a complex algorithm in JavaScript, I would likely make a lot of mistakes because I'm used to the compiler assisting me, right? So Haskell lets me express my ideas very concisely and nicely, and it lets me write software that I would normally not be able to write. And that's the reason most people write Haskell, because it's just too much work to write it in other languages. It's just too much mental arithmetic, and I tend to get distracted easily. And if I start writing code in other languages, I'll probably have lots of bugs, and I will not be a very good programmer. So it's easy to get this and slowly ramp up on the abstract stuff. It's quite possible. So yeah, I just wanted to, since we still have time, I wanted to display some examples of what abstraction in Haskell looks like. So we've seen how to create functions, how to create data types. We've seen some examples of why Haskell is better at doing some algorithmic stuff. But I wanted to touch base upon how you think functionally, right? So you have an algorithm, and how do you build upon it? How do you create abstractions, and how those abstractions are more than just create a function to do this one thing, right? So I'm gonna go over some of those. So the thing that we're going to start with is just summing numbers, right? It's a very simple problem. You have a list of numbers. I mean, you've not even a list of numbers. You want to sum all numbers from 1 to 10, right? And on the left is how you would do it in Python. So I've taken Python as an example, but any imperative procedural language, you would do it like this. You would have a total, you would have a counter, and then you would have a total variable, and you will count down from 1 to 10, and you would just add everything up in total, right? It's a very simple way of writing sum. And then you can do in functional programming, you can do it like this. So this doesn't look very functional, but I say it's functional because it's doing two things. It's creating a list of numbers from 1 to 10. So this bracket notation with dot dot, that's basically a way to create a list from of all numbers between two numbers that we've supplied. So this basically creates a list with all numbers from 1 to 10. And then there is a function called sum that basically works for any list, right? Any list of numbers, and then it adds them together, right? So again, as I said previously, looking at these two examples, even though the code on the left is very simple, you can't be absolutely certain that there are no bugs. They may be off by one error somewhere, right? Even in such a small, simple piece of code. But if you look at the Haskell example, then if the sum function works and if the list generation function works, then you know that this has no errors, right? The aim is to minimize bugs. So this is obviously much simpler. And what people generally say at this point of time is that, fine, this obviously has no bugs, but you've pushed all the complexity to the sum function. And the sum is defined in standard libraries, right? So it's not really a fair comparison. But the point here is that the point of abstraction is not to push things into functions, it's to generate a shared vocabulary. So sum is not just specialized to integers or to numbers, right? I mean, sum is specialized to numbers, but potentially we could write something that could work on strings also, right? Something that could work on any data type that can be joined together. And things that can be joined together are a special concept in Haskell called monoids, right? So I'm not going to go into that. But basically, I mean, this is not a special concept. It's just a name that people have given to things that can be joined together. So like strings are monoids, where you can take two strings and concatenate them together. Integers are monoids because you can take two numbers and add them together or multiply them together. So anything that can be joined together is a monoid, right? So we have functions in Haskell that basically work on any monoids. right? And as long as you have a function that can join two things together, you can join a list of them together, right? And I'm going to show you how that works, like in a couple of slides. But uh, so sum is a much higher level concept than it would seem just from this example. So sum is shared vocabulary. I call this shared vocabulary, right? And if you look at shared vocabulary on the procedural side, while is the only thing that carries from program to program, right? So looking at this, you recognize while, but everything else you have to parse and you have to figure out what's going on here. But on the right side, out of probably 10 characters, 5 of them are shared vocabulary, right? So it's really concise, and sum, list generation, so you know that this looks fine, right? So yeah, so this is how you would define sum. This is an example of sum, and this is specialized to ints. And if you read the type signature, it says take a list of integers and give me the sum, like an integer, right? And this is how you would naively define it. You would say that an empty list has the sum 0, and then if you have and this colon here is the same as const that we saw earlier. So here basically what I'm saying is sum of a list where the first element is x and the rest of the list is xs, then the sum is basically x plus and the sum of the rest of the list, right? So that should be fairly clear, right? That's the same as this while loop where we're saying where we're adding one element at a time to the total, except that in Haskell you don't have variables like total, so you define this mathematical equation, right? So I hope this piece of code should be very clear, where the sum of the entire list is basically the sum of the first element and the sum of the rest of the list, right? It's pretty simple. I mean, if this isn't clear, then let me know and I'll just open Notepad and give you an example. So yeah, so this is how you would do it. Now let's say the requirements change and you have to now multiply elements of a list, right? So again, you would write a similar kind of a program. You would say the multiplication of all the elements of a list when the list is empty is 0, right? Oh, actually it should be 1. I don't know why I wrote 0 here. Yeah, it should be 1 because 1 is the multiplicative identity of product. So yeah, so when there are no elements in the list, you would return 1, right? And you could potentially return 0, but then that's mathematically wrong, right? Because you might want to multiply two lists together, and the multiplication of the first list with the second list should basically be the same as multiplying each element individually. So the fact that the first list has no elements should not change anything. So if we return 0 for the first one, then everything will become 0, right? So ideally you would return 1 here, but that's more of a business rule. And again, you're writing the same thing where you're saying product of a list is basically the first element multiplied with the okay, there's a typo here. I should have written x into prod xs, right? So you're basically saying that multiplying all elements of a list is basically the same as multiplying the first element with the product of the rest of the elements, right? This is similar to a sum. So looking at these two, I'm gonna go back and forth very quickly here. So with sum and prod, you can see that they're basically the same code, right? The only thing that changes is that for sum you have a 0 for empty elements, for empty lists, and for prod you have a 1, even though this slide says 0, but for prod it should be 1. And for sum, when you take the first element and the rest of the elements, you combine it with plus, but in prod you combine it with star, which is multiplication, right? That's the only difference between these two pieces of code. So whenever you encounter such a situation in functional programming, you create a new function, right? Which takes all the things that are the same. So in this case, the same parts are what do you do when you encounter an empty list, and then you have to take the first element out and do something with the rest of the elements and then join them together somehow, right? Those things are the same. So abstract it out, and this operation is called fold. This is like a very common operation where you take a function. So now if you look at the function signature, it says that give me an element of type A and an integer, and I will give you an A, and give me a starting element, and give me a list of integers, and I'll give you the final result. So here, why do we have A's? So let's say the A is basically integer, right? So the first argument is how do you combine two integers together, right? I've given it a more generic type signature because fold works for general types. But let's say this A was int. That'll be much easier to understand, right? So here what I'm saying is first give me a function which combines two integers into one integer, and give me the starting integer and a list of integers, and I'll give you the final value. Right? So in case of sum, the way to combine two integers will be plus. In case of prod, the way to combine two integers will be multiplication, like star. In case of sum, the starting value will be 0. In case of prod, the starting value will be 1. And the list of integers will be the same, and I will give you the final result. Right? So we have defined this function that I mean, it may not seem exactly just by looking at it, but this does the same thing as this, right? Once you become more familiar with Haskell, you will realize that this is exactly the same as prod and sum. But basically, we've abstracted that out, and everything that changes, like the 0 and the 1 and the multiplication and the plus, we take as arguments. And some of them can be functions. That's fine, right? Because you can pass functions to functions. So you've defined a fold function, and then sum and prod become a lot simpler. Right? So just like with how we use sum to add 1 to 10 together, right? Sum itself is defined in terms of fold, which is even more generic, right? So sum is basically fold using plus and 0, and prod is fold using star and 1, right? And that does the same thing. And then once you have fold, you will realize soon that you can do more things with it. So you can say, if, for example, if you have a list of booleans and you want to see if any of them is true, then you will just write this function. Like this is or and false. So you start with false, and if any of them is true, then the entire thing becomes true, right? And similarly for all, if you want to check if all the booleans are true, then you start with true and you do and. So if any of them is false, then the entire thing becomes false, right? So that becomes easy to define. And then even for more things, like if are any elements greater than 3, if you want to scan a list and see if any elements are greater than 3, then you would still use fold again, and you would say the first function, originally we were passing just or, and now we're passing or with this check where e is greater than 3, right? So this is just the anonymous function syntax that we saw a while earlier. I mean, you can take a look at it later also, but it's still the same simple thing, right? Once you get used to the anonymous function syntax. So you can again define it using fold. And then if you want to check if any of the elements are digits or all of the elements are digits, like you're validating a phone number, for example, all digit is again written in terms of fold. You can easily write it like this, right? This is simple abstractions. Then you might think that, just by looking at these, any large, all large, and any digit, all digit, you again see similar code, right? In any large, you're doing fold with the you have an operation or here, and you have another operation that you do before doing or, right? So here it's greater than 3. And for all large, again, you're doing and then one more operation here, greater than 3, right? So, and here that instead of greater than 3, you're checking is digit instead of greater than 3. Otherwise, all the code is entirely the same. So abstract that also. So create, so I call this fold map. It's just some name I came up with. This is not a standard function. So I take two arguments. One is, how to combine ints, and one is this modification like greater than 3 or is digit or whatever, right? You take those two things and then you join them together using this, right? And this is again the same structure as this. It's kind of hard to see, but once you get used to this syntax, you will be able to see this, right? And then you can define any large and all large like this, like fold map or greater than 3 false, right? And fold map and greater than 3 false, like that, right? And similarly, any digit. So assuming, so if you, again, if you're looking at this code and you know fold map works correctly, fold map is correct, and you know it has no bugs, then this code also has no bugs, right? You can look at it and figure it out. So that's why, yeah, I jumped a slide, but why would you do this? So that you know that the code is simple and you've abstracted out code that you can test once, and then everything else, it'll be obvious that there are no bugs with it, right? And it's cleanly separated logic and reusable code that you can put in libraries. And it's easy to test functions in isolation. So you can test fold and fold map separately, and then you can test is any and all those functions separately. But when we did the second level of abstraction, we realized that now because we saw that there was one more thing that was being passed, we created another argument. So now fold map has 3 arguments, right? And if we discover another abstraction, do we add a 4th argument? I mean, how long can the argument structure be, right? So we don't want to keep on repeating this pattern. There has to be something else that helps us abstract this pattern. And when you become more used to functional programming, you will realize that there are ways of combining things that are not very obvious at first. So, for example, in this case, we can define a function called compose2, and this is literally the definition. Compose2 fmax is famx. Basically, it says if I have a function that f that basically works on a and then something else, then I can modify that something else and then pass it to f, right? So kind of hard to explain, but just by looking at the code, I mean, don't look at the type signature. The type signature is much longer than the code itself. But this is, you can define a composing function like this. And once you've defined that composing function, then instead of defining fold map separately, fold map itself gets defined in terms of fold, right? So then if you've defined fold map in terms of fold, then everything else becomes in terms of fold, right? So you can just say fold compose2 that you just defined, right? And you don't have to define fold map, and fold still has 2 arguments only, right? So we removed an extra function fold map which was not actually needed. Our existing machinery fold turned out to be powerful enough to support our logic, and we reduced code complexity, right? Because we introduced another generic shared vocabulary called compose2, which can be potentially used in other programs, right? But compose2 is still not perfect, right? Because compose2 is not in standard libraries. There's a reason for that, why it's not in standard libraries. And because there are better abstractions. So the thing about functional programming is that you will find abstractions, and they will be like decent abstractions, but they may not be the best abstractions. But someone else has already done the work of finding the best abstractions that you can just use, right? So in this case, the abstractions would be compose and curry, right? Currying. And someone else has already done the work, created those functions for you, created those libraries for you. So you are always learning new abstractions. And you can, once you understand an abstraction, you can use it anytime in your code. But that doesn't mean that you have to know the abstraction to be able to write Haskell. So you write code just like, you know, whatever seems natural to you, and then use whatever abstraction seems natural to you. And later on, you might realize, that abstraction that this guy wrote seems pretty cool, and I can apply it to my previous code, and then you can go ahead and change it. And Haskell lets you refactor things very easily, right? So refactoring is like a constant thing with Haskell. You keep on making it better and better. So a lot of times if you read open source code or someone else's code, you might think that this code is really smart. But usually what has happened is that they started off with something that just works, and that's kind of naive or dumb. And then they reiterated over it, refactored it, and until it became like really this pristine, shiny thing, right? Whereas with other languages, if it works once, you don't want to touch it because it might break something, right? With functional programming, you usually want to keep on changing it until it's perfect. So yeah, and by perfect, I mean not when you have put in all features. It's not features that make things perfect. It's when the code does exactly what it needs to do in exactly the perfect way. Doesn't have any extra code, anything complicated. Everything is simple, obvious. There's nothing that you can think of removing from the code. That's the functional language philosophy, right? So yeah. So this is how you do compose. This is even simpler than our compose 2. Dot is the compose operator in Haskell. I'm not going to go into specifically how this works, uh, but basically if you have a dot and you have another operator that's also generic called flip, then you can compose things using these two, right? And again, you see that instead of using compose2, which was one function, we compose it into two separate functions, right? Flip and dot. And that's a common pattern with functional programming. You keep on finding smaller and smaller units that work in a lot of different cases, and you keep on combining them together to get your logic working. And this style of programming where basically you're composing functions together, here I'm composing OR and isDigit together using dot, is called point-free programming. It's called point-free because a point is basically an argument, right? So this, you're taking a function and another function and joining it together without worrying about, without actually passing any arguments to them, right? So your unit of abstraction becomes a function rather than values, right? So that's called point-free programming, and it it sometimes makes things easier, sometimes makes things more difficult, but it's a common thing in Haskell to write code like this. And this would seem complicated if you're not used to it, but uh, on its own, it's a very simple concept, right? So this is the way you can look at it, right? Flip basically just flips a function's arguments around, and so if you're composing, if you're flipping this function, which is OR composed with isDigit, if you flip it, then the arguments AB become BA. They basically change the order of arguments. So flip of something AB is the same as that something BA. And then when you compose it, you're basically saying take the first function, take the rightmost function in that composition and apply that, and then take the leftmost function in that composition and apply that. So OR dot isDigit when applied to B and A will apply isDigit to B, and then it will OR it with A, right? So this is how this becomes this. It's like a data pipeline. It's very easy to see once you're used to it. But basically this is what's happening here. You're composing A or isDigit B using these generic combinators, right? Okay, so that's one thing, right? I've gone through a lot of details about functions and data definitions and how to join them and how it makes it easier, but we have not seen any examples of how this works with real world programs, right? We've seen toy examples like all these things are basically toy examples, like summing numbers from 1 to 10 is a toy example. How does it work when you have to join, like for example, when you have to access a database or print something out to the console? Those things are IO effects. How do you put those in? Right? So I just want to demystify that also. One of the purposes of this talk is to demystify that. And you can just clear your mind from this point and see how easy it is to do that, because it's actually easier than writing functions, right? So this is Haskell, right? And this is a monad, right? But don't worry about it being a monad, right? Think of it as any normal procedural side effects imperative language, right? So main is the function that gets called first, just like in C, and do is like begin and end, or parentheses or braces in other languages. So when you write do, you're basically saying do these things in order, right? And put strlen is a way to write a string to the console and then append a new line. So with a new line, so ln is new line, and what this does, as you can see, is basically it says it basically prints hello Haskell to the console, right? And if you just saw this, it would not seem intimidating at all, right? It's a very simple way of doing things, and Haskell has like the standard way of standard things, right? So so name here is, you can think of it as like a variable, right? So when you say so if you wanted to write a program which asks the user for its name and then says hello whatever the name is, so then this is how you would write it. You would say you would put the string, what is your name, then getLine is basically gets user input as a string until the user presses enter, right? And then you say getLine, and this is, so when you have equal to, that's basically mathematical equivalence in Haskell. But if you want that variable type behavior where you can assign things to variables multiple times potentially, then you would use this reverse arrow syntax. So reverse arrow means that, take this value and put it inside this variable, right? And this is not exactly a variable, but let's think of it as a variable right now, without going into monads, right? So this basically says, this seems simple, right? Show a string, then get the user input, and then show a string which says hello user input. And plus plus is the string concatenation operator here. So you can just print it like that, right? This is extremely simple procedural code. And Haskell lets you write code like this. So if you, and you can call functions in a similar manner. So let's say you wanted to abstract away this get name thing, which basically prompts the user for a name and then takes the name and returns that. You would write it like this. So, create a get name function which returns a string, and IO basically means that this function does side effects, right? So the side effects here are printing to the console and getting data from the console. So you would say do inside get name, do first print the string, what is your name, and then get the user input as get line, right? And then you can use this directly instead of doing get line, you can just do get name, right? And the syntax remains the same. Invoke get name and put the return value inside name, right? So this is like any other imperative language, right? You can write code with just IO and learn how to write code with just IO in a procedural manner and write proper Haskell code. You can do that. The only place where Haskell changes things is when, to write any real world program, you obviously have to write IO, right? But inside IO, you can call pure functions, which don't have this IO tag, right? So for example, plus plus is the string concatenation operator. That's a pure function. So you know that by doing plus plus, you can't have another side effect. Like it can't possibly change the value of the string name, right? Because plus plus is pure, right? So when you say hello plus plus name plus plus exclamation mark, you know that after this name will still remain the same. So those are the advantages that Haskell purity offers, right? So yeah, so similarly, more abstraction, you can say, show greeting basically just shows a name, and greeting is a pure function, string to string, which constructs that. So you can abstract away that pure part that I was talking about, the string concatenation, and this doesn't have the IO tag, and then you can use that inside IO. So the way you write a Haskell program is that you write like a spine of IO that can call pure functions. So you can't call IO from pure functions, but you can call pure functions from IO. And at the base, it's always an IO function. So this, if you look at this code, this would seem like any other programming language. Apart from the slightly weird syntax, this would seem like a normal code in any normal imperative language, right? So I just wanted to show you that even IO is not difficult in Haskell. And just to show you some quick examples of real world non-console, like in some languages console is easier, but when you think about databases or web servers, it becomes more difficult. So I have a few examples here also. I'm showing examples of my own code just because I happen to have a library which does server programming and also a library which does client-side programming. So I wanted to show you both. So YRoutes is a library for writing web servers, and you can just define a data type called route, which denotes all the routes in your application. So you can have a web app with a home page and a hello page, and you can just define it as a data structure. And now you get data type safety in your routes. So you can never have a link that doesn't exist in your page, right? So you just define that, and then it automatically creates functions called render route and parse route, and then you can do things like this, right? So this is again, very imperative code. So first you get the this is automatically generated, so you don't actually have to write this code. The server library YRoutes does this for you, but this is what it generates effectively. It says if the user is trying to access hello, then if it's a get, then call get hello, otherwise post hello. It's basically very imperative code. And then this is how you access the request details, like authorization header if you wanted to, and validate it or something. And you can set different statuses. You can do JSON stuff. So it looks very simple. Do is just whenever you see do, like $do is just basically starting new block of code, right? So here you're saying, so ignore run handler m. That's the function that basically runs the server. So it basically says that run this handler, and then inside the handler you're saying just get this request header and then validate this token, and if the token is valid, then send status, then send the JSON albums, and otherwise send error something. So okay, there's a typo here also. It should say if not is valid, then send 403, which is access error, and then send the error JSON. Otherwise, send JSON of the album data, whatever, right? So it's a very simple code. And another library that I wrote for for client-side programming is Concur, which is how you write. This compiles to JavaScript. So how you write client-side applications, single-page applications, and this is how the code looks. So here you're saying get a random number. Ignore this part, the first part, which is basically like a shortcut way of writing do notation. Do notation compiles to this, right? So I've just written it like that. But basically you're saying, again, you can look at this, right? So it says first show the user a div. Inside it, there's a text box. Inside it, there's some text, which is try to guess. And then there's an input enter, like a text box. And then when the user enters this, it goes inside the guess string, which is a variable. And then try to read the value of the variable as a number. And if it's nothing, which means that it wasn't the correct number, it wasn't parsable as a number, like user wrote ABCD, for example, or an empty string, then it just says goN. goN is basically a recursive call to itself. Like goN is this function that I've defined. goN is equal to do. So it says just restart the program. And if it was just guess, which guess is a number, then if guess is smaller than the initial number that we wrote, then show a div with text go high, and otherwise show a div with text go low. And if it's the same, if it was equal to the secret number, then show a text you guessed it, and then a button to play again, right? So you can see how simple writing. And by the way, if you didn't figure it out, this is the high-low game where the program selects a secret number, and then you have to enter a number, and then if it's higher, then the program tells you whether it's higher or lower than the secret number, and you have to keep on guessing until you get the exact number, right? So this is that game, the entirety of that code, except maybe type signatures and some imports and stuff. So this is the entirety of that code, and it will give you a single page application that shows you a text box with some text and lets you play that game over and over and over again, right? So apart from syntactic issues, this should be very simple. And this is based on React, this particular example. I mean, I have a bunch of backends, but you can use React. This is like a binding to React. So the point of this is that you can do real world stuff in Haskell, which is again just as concise as like proper pure functional programming, right? So so I had these 2-3 slides. If we have extra time, I don't think we have enough time to cover like functor, foldable, those kind of things. But maybe for another session later on. But I hope I've given you guys enough of context on, how to, write functional programs, and given you enough context to explore on your own. And, I hope you guys join the FP-NCR group. And if you have any questions, you can contact me directly or through the group or wherever. And I'll be happy to answer. So I'll be happy to answer any questions if you guys have any at this point. While I still have 3 minutes, I can show you guys one more thing. So I was talking about this language called Clean, which I don't have right now, but so I just wanted to show you how good the Clean IDE was. It's kind of old right now, but it's just I wanted to show you how a couple of hundred lines of functional programming code uh, can do something really amazing. So this is basically clean code. This is not Haskell, but it's very similar to Haskell, and the code is like, I don't know, maybe 500 lines. That's my guess. And this is basically a full Scrabble game with an AI and everything, right? So Clean had really good IO libraries, like GUI libraries and stuff. So and this is code from like uh, I guess probably late 90s or early 2000s. So so this was available then, and most languages are still discovering all these abstractions. So yeah, Haskell is also still not there. I mean, when it comes to GUIs and stuff, Haskell is still not there where Clean was at that time. So yeah, this is the Clean IDE. It's kind of bare bones, but it seemed pretty good at that time. Yeah, so that's my presentation. Thanks everyone for attending. I think we're also out of time, pretty much. So yeah, I'm happy to take any questions. I'll go back to the FPNCR thing just in case anyone wants to join. These are the links. So we have a Slack channel. You can join this functionalprogramming.slack.com, which has a lot of other groups for other functional programming languages. But if you wanted to join the FPNCR group, that's the channel FPNCR. Okay. Okay. Thanks, guys. Thanks for listening. I'm gonna disconnect. Thanks. The slides will also be available somewhere. I'll see if there is a way to upload the slides, and I'll upload the slides somewhere. So, or maybe I'll just put them on GitHub or something, so everyone can access it. Cool. Okay, thanks everyone.